Hello and welcome back to our video series on astronomy. My name is Mr. Nelms and I am one of the physics and astronomy teachers here at Haberdashers Adams. In this second episode we will look at solar and lunar eclipses, how they occur and what they look like from Earth.
3, 2, 1.
We choose to go to the moon.
There are two types of eclipse that can occur with our moon, a solar eclipse and a lunar eclipse. Please note that the upcoming images are not to scale, as the real moon is much further away from the Earth than we're about to see, but that would not show up particularly well in one image together. Solar eclipses happen when the moon is directly between the sun and Earth, causing the shadow of the moon to block out the sun's light for observers on some of Earth's surface. People who are within the umbra of the shadow on Earth will have the sun's light almost completely obscured by the moon, with only the atmosphere of the sun visible around the moon. Incidentally, this is one of the few times that we can see a new moon in the sky, though this does play second fiddle to the much more dramatic effect of the eclipse itself. When viewed from Earth, those in the umbra or full shadow of the moon will see a total solar eclipse. Due to lucky circumstances, the diameter of the sun is approximately 400 times greater than that of the moon, but it is also around 400 times further away from the Earth than the moon is. This means that the two objects have a very similar angular size when viewed from Earth. This means that they take up the same sized angle in the sky. And the moon almost completely obscures the sun during a total solar eclipse. If you are lucky enough to see a total solar eclipse for yourself, then there are a few things that you might want to look at more closely. First is the corona of the sun. This is the outermost region of the sun's atmosphere. It is incredibly hot at temperatures exceeding 1 million degrees C. It can be studied by astrophysicists to understand the sun's magnetic field, the solar cycle, and events like solar flares. You can also observe a diamond ring effect in the 15 seconds before and after totality, which is the point when the moon is completely in front of the sun. At this stage, there's slightly more of the sun's corona visible, which gives this effect. And you will also be able to see Bailey's beads. These look like small blobs of light at certain points along the edge of the moon's surface and are actually formed by the sun's light passing between valleys on the moon and the lunar mountains.
Obviously, we all know that looking directly at the sun is not a good idea, and this is no different during a solar eclipse. The sun's light can significantly damage your eyesight and even cause blindness with prolonged exposure. To keep yourself safe, you need to wear a pair of eclipse glasses. Now, if you are observing the eclipse through a telescope, then there are two ways that you can protect yourself. The first and cheaper of the two methods is to project the image onto a piece of paper. For this, you'll need to block off around the end of the telescope to prevent light from spilling onto the paper directly from the sun or other light sources. From there, you simply position a piece of paper beyond the eyepiece of your telescope and look at the eclipse on this. Secondly, you can install a hydrogen alpha filter to the front of your telescope. This has some similarities to the eclipse glasses from earlier, but rather than reducing the intensity of light, they reduce the range of wavelengths of light that come in. This allowed a past student of Adams to create this series of photos during the partial solar eclipse of March 2015.
Finally, we have the lunar eclipse. Here, the shadow of the Earth falls on the lunar surface, blocking out the sun's light. This can only occur when the moon is in the full moon position. To produce a lunar eclipse, the moon needs to enter into the umbra shadow of the Earth. As the Earth is larger than the moon, it casts a larger shadow. This means that lunar eclipses occur more frequently than solar eclipses and will last for a longer period of time. When viewed from Earth, the moon will become significantly fainter as the sun's light is gradually blocked from reaching it. Interestingly, the moon appears red during totality when it is completely in the Earth's umbra. This actually happens because of the same process that causes the sky to be blue, which is something called Rayleigh scattering. The sun emits light across the entire spectrum, and as the light passes through the atmosphere of the Earth, it can interact with the particles in the air, causing the light to scatter. The shorter wavelengths of light, like blue and violet, are scattered more. This makes them more likely to scatter into our eyes than other colours, which is why when we look at the sky during the daytime, we see it as blue. As the shorter wavelengths are more likely to be scattered, this means that the longer wavelengths, like red and orange, are more likely to pass through the atmosphere without deviating from their paths. This, coupled with the fact that the light will refract or bend slightly as it passes into the Earth's atmosphere, will allow some of the sun's light to bend around the Earth. With red and orange light being scattered less, it is this light that is able to reach the lunar surface. This is the only light to reach the moon from the sun, as the rest is blocked by the Earth itself.
Now, while it is great to see a lunar eclipse just for the spectacle of it, you may be wondering what scientific benefits there are and what can be proven from this phenomenon. There are actually several things that we've learnt from observing lunar eclipse, but I'll give you 2 for today.
First up, proof that the Earth is roughly spherical. Sorry for all the flat earthers from all around the globe who have made it this far into the video without getting upset, but the Earth is indeed round. We can see this by studying the shape of the Earth's shadow during a lunar eclipse. Only spheres, or oblate spheroids in the case of the Earth, cast a curved shadow regardless of the direction that the light is coming from. Secondly, we can determine the relative size of the moon compared to the Earth. This was worked out by an astronomer by the name of Aristarchus over 2,000 years ago by considering how the shadows formed during a solar eclipse would compare to those in a lunar eclipse. Now, I'm not going to go into full detail on this, that would take a whole video on its own. But in short, both the shadow of the moon during a solar eclipse and the shadow of the Earth taper by roughly the same amount, which is approximately the diameter of the moon. Aristarchus used this, along with the time taken for the moon to enter and exit the shadow of the Earth compared to the time taken during totality in a lunar eclipse, to determine how large the moon was compared to the Earth. He found it to be around 1/4 of the diameter, which is a very accurate measurement considering the quality of equipment that he had at his disposal.
Now, whilst those 2 examples are not exactly modern, there is still new scientific ground being broken with each lunar eclipse, with satellites like the Lunar Reconnaissance Orbiter able to take a much closer look at the moon. It has taken the opportunity to see how the lunar surface reacts to the rapid temperature drop and rise that happens during a lunar eclipse. This will hopefully give us more information about the surface and structure of the outer layers of the moon, including a greater understanding of where there may be concentrations of subsurface ice. And that concludes our second video in the lunar series. There is plenty more to learn about eclipses, so if you've enjoyed this video, please do continue to explore this topic further.
If you want a good starting point for what to look into after this video, you might want to consider one of these 3 options. 1. Why don't solar and lunar eclipses happen on a monthly basis? 2. What is an annular eclipse? And 3. What would a solar eclipse look like on a different planet? Thank you so much for watching, and hopefully you'll join us next time where we'll be looking at the key features of the lunar surface and when it is best to observe them.